Action. I think lasers and medical shouldn't be said together anyway. Okay, so we have the crow flying horizontally. Guys, shh, hey. Guys, let's go. We have the crow flying horizontally. True story. These animals actually basically use gravity as a tool. They drop things to break them open and get food from inside them. So we have a crow flying horizontally at 2.70 meters per second when it releases a clam from its beak. The clam lands on the rocky beach 2.1 seconds later.
And then a seagull gets there.
That happens sometimes. What do the seagulls say in Finding Nemo? Mine. Exactly. Great. This you guys know.
Is that going on the film?
2.10. 2.10 seconds later. Just before the clam lands, what is the horizontal component of its velocity? And B, the vertical component of its velocity. Okay, so here's what happened. For now, these two equations should still work. These are actually displacement equations.
Yeah, but you gave us a different one. You gave us x equals v initial t.
Okay. Yeah, that's because for all of our examples yesterday, we were able to have x sub 0 be 0. We were able to pick what it was. But this one's actually a little bit... Again, this problem's not really that hard if you keep thinking in terms of independence. Vertical and horizontal motion are totally independent of one another. Okay? So the horizontal motion just keeps going on forever until it hits something. So here's the crow. Looks a lot like a gull. It's flying. It releases the clam.
It has no head.
It has no head. When it releases the clam, all it's doing is going horizontally at 2.70 meters per second. Okay? Correct?
Yes.
Now, after it releases, the instant it releases the clam, that's all that's going on. And since we're ignoring air resistance, and clams aren't known for having a whole lot of air resistance anyway, that's going to keep happening. What starts happening in addition to this?
If it's open, it does have gravity.
That's true if you opened it. But if it were open, why would the crow need to drop it?
Because it's empty.
It's a slow
All right.
Or maybe like the clam was like closed.
Stop. We're not speculating on clam motivation. Clam or crow motivation.
In the middle school.
Anyway, here we go, guys. Shh. Guys. Now, at this point, all that's happening is this horizontal velocity. An instant later, we have the horizontal velocity and this much and some small amount of gravity affecting it. After that, we've got the same horizontal velocity and more gravity affecting it. And then we've got the same horizontal velocity and gravity will be accelerating it even faster.
I totally feel like that's not what the clam does.
No, the clam actually does something like that. The clam does something like that, and it winds up going on a curved path because the horizontal velocity stays the same as the vertical velocity keeps increasing. That's what gives its path its curve. Otherwise, we'd just be adding two vectors like last chapter, and we'd be done. That would be all the clam would do. But since gravity is an acceleration, it doesn't work that way.
And why, when you're like writing on a convertible, if you spit and it comes back to you?
Wind. Because that doesn't happen in an enclosed car. That's just air, which we're ignoring for this course because you need to be through like 3 semesters of calculus to start talking about air. Yeah, but if you're in an enclosed car where the wind isn't rushing past you and you spit, it just goes wherever you spit.
Why would you?
How often do you spit in convertibles?
Alba spits a lot.
Apparently. Okay.
She's driving too.
Now, this is what the clam's doing. The point is these two things can be thought of as totally independent. Now, question A says, what is the horizontal velocity of the clam? Well, what was the horizontal velocity of the clam to begin with?
2.7 meters per second.
And since
2.70.
And since we're ignoring air resistance,
thank you, Alba.
When it hits the rock, it's still, guys, when it hits the rock, it's still going to have that horizontal velocity.
It hits a rock?
Yeah, they're dropping it on a rocky beach. That's what the problem says. So when it hits the rock, it still has that horizontal velocity. In addition to that, it has some vertical velocity. What is its vertical velocity? This is another question that actually doesn't require a lot of math. Well, it does, some, but...
Negative 21.63
Yeah,
meters per
that's what I
second.
got.
How'd you get it?
I got it,
put
no,
2.10
with the y, yeah.
into times squared and
Stop, guys, stop.
multiplied it by the reciprocal.
Stop.
And
Hey, Ramsey, stop a sec. Wait a minute. Did you use this equation?
Yeah, I got 1/2 times 9.81 times 441, which is 2 times squared.
Okay. That actually gave you how far it fell. That answer should have been just meters, right?
Yeah.
If you check out the units. The question was, what was its vertical velocity? How fast was it falling at that second? The crow really doesn't care how far it goes to hit the rocks. What the crow cares about is how fast it hits the rocks. Because that's what's going to determine how it breaks it open.
Oh, so we just put time in for acceleration for 9.81?
Acceleration times time, yeah, 9.81 meters per second squared times 2.10 seconds. Seconds will cancel, and acceleration times time will get you the velocity. That's one of the older equations we used a little while back.
20.601.
That seems reasonable. So 20.6 with the correct significant digits, meters per second. Isn't that close to what you got?
Yeah.
So the speed, by coincidence, the speed and the
Yeah,
velocity and the distance turn out to be very similar.
21.6.
But yeah, 20.6 meters per second is the velocity you're looking for, because you multiply acceleration times time to get velocity. It's dimensionally consistent. So that's how fast it hit. C. How would your answers to part A and B change if the speed of the crow were increased?
Only the answer to part A would increase.
No, the y would increase.
No, just horizontal
Just
because
A would increase.
horizontal and
Kath, go ahead.
vertical have no bearing on each other.
True, horizontal and vertical have no bearing on each other. So if the crow's going at 1 meter per second or 50 meters per second, the clam falls down at the same speed.
As long as
But-
the height stays the same.
As long as the height stays the same. Very good. Kath, you got this. Okay. Why are you asking for my help second period? You got this.
Well, I don't.
Answer is
A would increase.
vertical. I wish I had a larger board. Vertical velocity. Here, I can write it smaller. I'll have to erase this.
Not the stairs.
Okay, not the stairs, I know. The answer is v sub x would increase. V sub y would stay the same as long as the height stayed the same. And then 16, there is no 16D.
That's
Okay.
what I wrote.
Good.
You see.
Any questions on 16 before I go on to something slightly new and exciting? Unfortunately, declining is not an option.
No.
Darn.
Darn it, I know.
Mrs. Punjab.
Thank you, Ramsey. Okay,
Don't you mean Mr. Punjab?
yes. Now,
Is Punjab Indian?
it's actually, yes, it's from the Indian subcontinent, but they don't consider themselves to be Hindi or Muslim. Prominent ethnic group is the Sikhs. Actually, they're the ones who actually wear the turbans,
Cool.
don't shave their beards, have some really cool religious views.
Because this is what we learn in physics.
Okay, so today we are going to learn new notes. The parametric
Oh god.
equations
What's that?
for ballistic trajectory.
Yes, this is so cool.
I think so. Parametric equations for ballistic trajectory.
Can we use the catapult now?
Eventually. You earn it. Alright,
You earn it.
ballistic trajectory means, okay? Ballistic trajectory is a fancy way of saying whatever you've thrown into the air has no independent way to fly. You are not talking about a rocket, a Superman, a bird, a plane.
Or Ramsey / Jesus.
Yes, we're not talking about any of those things. We're talking about a cannonball. We're talking about a bow and arrow, although wind resistance really messes with bows and arrows.
Mr. Punjab.
We're talking about bullets. We're talking about